Algebra by Michael Artin. Section 10, Quotient Groups. We saw in the last section that the congruence classes of integers modulo n are the cosets of the subgroup nz of z+. So addition of congruence classes gives us a law of composition on the set of these cosets. In this section, we will show that the law of composition can be defined on the cosets of a normal subgroup n of any group G. Addition of angles is a familiar example of the quotient construction. Every real number represents an angle, and two real numbers represent the same angle if they differ by an integer multiple of 2 pi. This is very familiar. The point of the example is that addition of angles is defined in terms of addition of real numbers. The group of angles is a quotient group, in which G equal R plus and N is a subgroup of integer multiples of 2 pi. We recall a notation introduced in section 8. If A and B are subsets of a group G, then AB equal the set AB such that A is a member of A and B is a member of B. We will call this the product of the two subsets of the group, though in other contexts the term product may stand for the set A cross B. 10.1 Lemma. Let n be a normal subgroup of a group G. Then the product of two cosets, an and bn, is again a coset. In fact, an times bn equals abn. Proof. Note that nb is equal to bn by 6.18, and since n is a subgroup, n times n is equal to n. The following formal manipulation proves the lemma. An times bn equals A times NB times N equals A times BN times N equals ABNN equal ABN. This lemma allows us to define multiplication of two cosets C sub 1, C sub 2 by this rule. C sub 1, C sub 2 is the product set. To compute the product coset, take any elements, A a member of C1 and B a member of C2, so that C1 is equal to AN and C2 equal to BN. Then C1, C2 equal ABN is the coset containing AB. This is the way addition of congruence classes was defined in the last section. For example, consider the cosets of the unit circle n in G equal C star. As we saw in section 5, its cosets are the concentric circles. C sub r equal the set Z such that the absolute value of Z is equal to R. Formula 10.1 amounts to the assertion that if the absolute value of alpha is equal to R and the absolute value of beta is equal to S, then the absolute value of alpha beta is equal to RS. C sub R times C sub S equal C sub RS. The assumption that n is a normal subgroup of G is crucial to 10.1. If H is not a normal subgroup of G, then there will be left cosets C1, C2 of H in G whose products do not lie in a single left coset. For to say H is not normal means that there are elements H a member of H and A a member of G, so that AH A inverse is not a member of H. Then the set 10.2 AH times A inverse H does not lie in any left coset. It contains A1 A inverse 1 equal to 1, which is an element of H. So if the set 10.2 is contained in a coset, that coset must be H equal 1H. But it also contains AH A inverse 1, which is not in H. It is customary to denote the set of cosets of a normal subgroup n of G by the symbol 10.3. G divided by n equal the set of cosets of n in G. This agrees with the notation Z over NZ introduced in section 9. Another notation we will frequently use for the set of cosets is the bar notation. G over n is equal to G bar and AN equal A bar, so that A bar denotes the coset containing A. This is natural when we want to consider the map 10.4, pi mapping G to G bar equal G over n, sending A to A bar equal AN. 10.5, Theorem. With the law of composition defined above, G bar equal G over n is a group. and the map pi, 10.4, is a homomorphism whose kernel is in N. The order of G over N is the index G:(n) of N in G. 10.6 Corollary. Every normal subgroup of a group G is the kernel of a homomorphism. This corollary allows us to apply everything that we know about homomorphisms to improve our understanding of normal subgroups. Proof of 10.5. First note that pi is compatible with the laws of composition. Since multiplication of cosets is defined by multiplication of elements, pi of A times pi of B equals pi of AB. Moreover, the elements of G having the same image as the identity element 1 are those in N. 1 bar equal 1n equals n. The group axioms in G bar follow from Lemma 10.7. 10.7. Lemma. Let G be a group and let S be any set with a law of composition. Let phi mapping G to S be a surjective map which has the property phi of A times phi of B equal phi of AB for all A and B in G. Then S is a group. Proof. Actually, any law concerning multiplication, which holds in G, will be carried over to S. The proof of the associative law is this. Let S1, S2, S3 be members of S. Since phi is surjective, we know that S sub I equal phi of A sub I for some A sub I a member of G. Then, quantity S1, S2 times S3 equal quantity phi of A1 times phi of A2 times phi of A3. Is equal to phi of A1, A2 times phi of A3 is equal to phi of A1, A2, A3 equals phi of A1 times phi of A2, A3 equals phi of A1 times the quantity phi of A2 times phi of A3 equals S times the quantity S2, S3. We leave the other group axioms as an exercise. 10.8 Figure, a schematic diagram of a coset multiplication. For example, let G equal R star be the multiplicative group of non-zero real numbers, and let P be the group of positive real numbers. There are two cosets, namely P and negative P, equal the negative reals, and G bar equal G over P is the group of two elements. The multiplication rule is the familiar one. Negative times negative equal positive, and so on. The quotient group construction is related to the general homomorphism phi mapping G to G prime of groups as follows. 10.9 Theorem. First isomorphism theorem. Let phi mapping G to G prime be a surjective group homomorphism, and let n equal the kernel of phi. Then G over n is isomorphic to G prime by the map phi bar, which sends the coset A bar equal an to phi of A. Phi bar of A bar equals phi of A. This is our fundamental method of identifying quotient groups. For example, the absolute value map of C star to R star maps the non-zero complex numbers to the positive real numbers, and its kernel is the unit circle U. So the quotient group C star over U is isomorphic to the multiplicative group of positive real numbers, or the determinant is a surjective homomorphism GLNR to R star, whose kernel is the special linear group SLNR. So the quotient GLNR over SLNR is isomorphic to R star. Proof of the first isomorphism theorem. According to proposition 5.13, the non-empty fibers of phi are the cosets an. So we can think of G bar in either way, as the set of cosets or as the set of non-empty fibers of phi. Therefore, the map we are looking for is the one defined in 5.10 for any map of sets. It maps G bar bijectively into the image of phi, which is equal to G prime because phi is surjective. By construction, it is compatible with multiplication. Phi bar of AB bar is equal to phi of AB equal phi of A times phi of B equal phi bar of A bar times phi bar of B bar. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renholt with programming and illustration by Jim Renholt 2019. Thank you for listening.